to add on to our lesson on multiplying algebraic expressions, we're going to talk about perfect squares right now. And this won't be too long. Remember, a perfect square just means anything that is being squared, right? So in this case, this is x plus 5 all squared. Sometimes we say quantity squared, right? Before we get to that, quick thing, prior knowledge for this is what an identity equation is, because we'll use that here in a moment. So for example, if I had, we'll use something we've talked about recently, 3 times x plus 5, we know that if we distribute, we get 3x plus 15. Okay, and I want you to be really carefully think about this. This left one is honestly different, especially the order. This says take a number and add 5, and then afterwards multiply by 3. Whereas this side says take a number and multiply by 3 first, but then after that add 15. So you notice it's not adding 5 again, right? So these fundamentally are just a different order from each other, but it turns out they always produce the same outcome as each other, the same output if you put an input into them, right? If we think about each side as a separate function, any input, if you put the same number into each, it always produces the same outcome, okay? That's really important. So let's get to this particular example. X plus 5 squared. If I asked you really quickly to simplify that in your head, go ahead and do that. My guess is a lot of you might be able to come up with what you think the product is, or, you know, if we expanded it, what it is. I think a lot of you might be saying this is simply x squared plus 5 squared, because we just put the squared in there. I'm going to question that. I'm going to put a question mark here, because I'm not really quite sure if that's going to work. Well, if we have something we think is an identity, or true, what can we always do here to test it out and really see? We can plug numbers in, right? So what if we actually tried this out? Think of a number, let's say 2. Why don't we try 2 plus 5 squared and see if that's equal to 2 squared plus 5 squared, right? We're testing it to see. And again, I'm going to, put that there because I'm not sure if it's exactly true. And again, watch this. 2 plus 5 ends up being 7 squared. And this ends up being 4 plus 25, which gives me 29 and 49. And I still have my question mark all the way to the end, but carefully look at that and we can clearly see that's a not equal, right? So plugging numbers in is a really important way to test things out. It turns out x plus 5 all squared, it's not x squared plus 5 squared. Part of it is correct, but you'll see if we use expansion boxes or distribution like we talked about, you'll see that it actually is going to be a little bit different. There's a piece that's missing essentially. Actually, technically there's 2 pieces that are missing, okay? And part of the reason for this is, remember that exponents themselves are based on the operation of multiplication. And since that's addition, an exponent cannot distribute across addition. The only way that works is, again on the side, if I instead had x times 5 squared, then we could do x squared times 5 squared, because you can think that this is x times 5 times x times 5. And I have 2 x's and 2 5's. But since it's all multiplying, there's no other operations mixed in there, then this is okay, but this is not, okay? So here's what I want you guys to do. Just a few more notes to add on, and we'll do what this really equals, and then a couple more examples of that. So we found out that that is no. But what is it really equal to? Let's go ahead and just give our instructions. We're going to multiply each of the following. So let's just use our expansion box. And maybe you've become good at doing this in your head already. And if you have, that's awesome. Doing things in your head is great. Well, I get x times x, which is x squared. And then that 5 times 5 actually shows up, 5 squared. I'll just write it as 25. But you'll notice there's 2 pieces missing in our distribution here. When I distribute this x to the x and the 5, here's 5x. and then distribute this 5 to that x and 5, I get 5x and 25. So it turns out we have two 5x's here, and this is actually equal to x squared, and it's gonna have that 5 squared, that 25, but 5x and 5x together gives me a total of 10x. So actually this is equal to x squared plus 10x plus 25 rather than just x squared plus 25. Okay? So doing a couple more of these yourself. You may try this one. Let's do 2x plus 3 squared. Okay? And again, you can just pause this real quick and try it yourself. Well, this one's going to be a little trickier if you try to do it in your head, but I think I can do it in my head. You should get 4x squared plus 12x plus 9. And if I do my 2x plus 3, you can see 2x times 2x is 4x squared. And then I get a 6x, but then I get another 6x. You'll notice these two things end up being the same, don't they? But it's because this and this was the same. Only in the case where we're talking about perfect squares, of course. And then I get 9. So again, it's not just squaring the two individual pieces. You have to include what's in the middle, and 6x plus 6x is 12x. Okay? So again, make sure that's correct, and you're good with that. And we'll call it good for there, but we're going to make one last example. In fact, we're going to generalize this and see if we can notice patterns. And we're not going to use like just a letter and a number. We're going to use both A and B and see if we can find a rule for this. So again, if you use an expansion box, go ahead and pause and do that yourself. And we'll see that if we do A plus B multiplied by itself, here's my A squared and B squared, kind of like you thought. But remember, we got two other missing pieces. If I distribute this A into the B, I get AB. And then this B into the A is BA, but you probably recognize that it's the same as AB. And yet again, these two things are the same. So when we add all the boxes together, I get A squared. And if there's an AB and another AB, how many of them are there? 2 ABs plus B squared. And this actually turns out to be really helpful because if you notice this, this is like my A and my B. So if I have A squared, and then I have 2AB, and then here's my B squared. So we have the things that are squared like we expected, but the middle should be 2AB, which means, because you notice there's just two pairs of these two things multiplied together in every one of the expansion boxes. So 2x times 3 is 6x. Remember that 6x? And then 2 of those makes 12x, because these always are ending up the same, these two boxes here. And you always have 2 of them. That's where we get the 2AB. So again, we can see that. Where does 10x come from? Well, again, if this is my A and my B, what's 2AB? 2 times x times 5. It's 10x. So again, this is like my A squared and my 2AB and then my B squared. Okay? So that's a nice little pattern.